Okay, this is chapter 4, extension number 3, where we're going to look at graphs of relations and functions. I hope that you remember this terminology. Domain, of course, is the set of values for the independent variable. Or you can say the x values on a graph. The range, yes, that would be the dependent variables, or the y values. Okay, so, example number 2. What happened to example number 1? Well, let's pretend this is the one then. So example number 1, it says we can represent a function that associates every number that is 1 less than triple its value. 1 less than triple its value. What do you think the equation then looks like? 1 less than triple its value. So if I triple a value, that's like 3x, right? If I subtract 1, 1 less, minus 1. So perhaps an equation looks like this. Now, I'd like you to graph out this function using only whole numbers for x and y's. Okay? Which means I'll make a quick table of values. I'll choose some whole numbers for x and y. 0, -1. 1 would be, I guess, 2. 2 would then be 5. 3 would then be 8. Right? And if I did it on this little grid here, let me quickly draw my axes. X, Y, 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5, 6, 7, 8. So each are 1 unit. And so if I plot 0, -1, that'd be, remember, whole numbers for both x and y. Not a whole number. Not whole number. Therefore, I can't graph this out. So only points I can graph out are 1, 2, 2, 5, 3, 8, and I guess so on. Okay? Now, in part B, though, I said, look, graph the function of both x and y that are real numbers. Real numbers can be positive, negative, decimals, everything in between. So if you think about that, I better change where my axes is. I'm going to now change it to like somewhere here, perhaps. Okay, x, y, once again, 1 unit, right? 1, 2, 3, 4, 5. Now I can plot 0, -1. That's right down here. I can plot 1, 2, 2, 5, and so on. But this time, because I'm asking for real numbers, which I said includes everything, all the decimals, I can now join them together and also put arrows on the end to say that it goes on forever and ever and ever. Okay? Now, with that, can you actually now talk about the domain and range of both of these graphs? So the domain for the one on the left, which are just whole numbers, would be x belongs to the set of not just whole numbers, but natural numbers, because I didn't have 0 included. Now, by the way, I don't know if you have a textbook in front of you, but if you do, some textbooks have a formal way of writing domain, and let me show you that right now. It's not just the stuff in red, but they say this. X belongs to the set of numbers, where x is a set of real numbers of n, and they have these squiggly brackets over here like this. Okay. For my purpose, I'm just okay with you having written down the stuff in red, but if you're curious, this is the actual formal way of writing it. So similarly for range, it'd be squiggly bracket y, the bar, and in this case, I can just list out the numbers. So I can just say 2, 5, 8, ... Or if you want to use a formula, another way of doing it would be, once again, the formal way. But if you want the formula, just say something like this. The y is equal to 3x - 1, where, of course, in this case, x is a natural number, which also implies that y is a natural number. Okay? A little bit tricky to write, so sometimes it's just really easier just to list them out. Okay? Now, just to let you know, this is an example of what I call discrete data, where the points on the graph are not connected. because the values in between them have no meaning. Okay? I can't have 2.5. I can't have 2.35. All right? Now, for the one on the right here, the domain, yes, that is just all real numbers. And if you want the formal way of doing it, then x is like that. And the range, yes, also includes real numbers. So I'll use this R to represent real numbers. And there you have it. Okay? Now, in this case, this is an example of what I call continuous data, where the points on the graph are connected by a solid line or curve, because all the points in between also still have meaning. Okay? So, hopefully you can see the difference. Discrete data, continuous data. All right. Some more review of function terminology. Remember this idea of a function? Said it many times. I think I said it in the first video, second one. Now I'm saying it's the third one. A function, once again, is a relation where each element in the first set is associated with, that's right, only one element in the second set. So now I'm going to add on this extra question. Not only do I want you to find domain and range, but tell me if this is a function or not. Okay. So domain for the temperature in this case, I guess it's time. I look at the dots. I guess in this case I'll just say the dots are at 3, 6, 9, 12, 15, 18, 21, 24. It's just easier to list them out. And the range, yeah, probably easier to list that out. Temperature, perhaps. Maybe I'll go capital T this time. And what are the values there? Maybe like 5, I think maybe 6. I'm a little bit estimating, but you know what? You can do the same thing. 18, maybe 22. I think that's good enough. Right? Now, is this a function? For each x value, is there only one y value? The answer is yes. Good. Okay. You try part B on your own. Okay? Go for it. I said go for it, so don't wait for me for the answer. Okay, I'll give you the answer now. X values, -3, -1, 1, 2, and 4. The range, once again, is the y values. Will go from smallest to largest. I'm thinking 0, 1, 3, 4, and 5. Now, this is the interesting question. Function or not? So for each x value, is there only one y value? And this is a problem right here. Look, for the value of x, which is 4, there's a y value of 0. There's also a y value of 3, and there's also a y value of 5. That is a problem. Therefore, no. Right? The x value of 4 has multiple y values, and that is not good. So my question to you before we turn the page is, how can you tell if the graph is a function or not then? Is there some kind of test that we can actually use to determine if it's a function? And the answer to that is, you bet there is. So to determine if a graph is a function, there's something called a vertical line test. Yeah. So the key is, if no 2 points on the graph can be joined by a vertical line, then the graph is a function. So all you need to do is place a ruler vertically on the graph, or your hand, just a vertical hand, and slide it across the graph from left to right. If the edge always intersects the graph at no more than 1 point, then you're okay. It's a function. But if that vertical line intersects the graph at more than 1 point, at 2 or 3, then definitely this is not a function. So understanding that, let's see if you can quickly tell me which one of these graphs are functions and which one is not. Is the one on the left a function? Well, let's see what happens if I draw vertical lines. Yeah, only touch 1 point, right? So therefore, yeah. Ooh, no way. Now this one over here is good, but once I put a vertical line here, ooh, bad news. So no way. And this one is interesting. You see this solid dot and an open dot? You're like, what's going on there? An open dot means it gets closer and closer to this, but it's actually not a value. The actual value at that point is the solid dot. So if you think about drawing lines, yes, only one, only one. Now if I draw it right here, yes, there's only one, so it's still okay. So for this one, yeah, it's still a function. Okay? So just drawing the vertical line test will show. Okay. Oh, by the way, if I were to change the graph of the last one, let's say I had a solid dot here and a solid dot here. So yes, 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 yes. Right here. No. So this one would not be a function. Okay. So with the next examples here, it's the same deal. I want you to practice finding domain and range of each relation and then determine if it's going to be a function. Alright? A lot of graphs here too. Okay? So I'll quickly do the first few, but I want you to try some on your own. Alright? You've got to try them on your own because that's how you actually learn. Not by listening and just watching me, but by actually trying them on your own. X values, what are they? 2, 5, 7, 9. Range. Y values, what are they? 5 and 7. For each X value, is there only one Y value? You bet. So therefore, yes, it's a function. Okay. How about part B? You try this. It's the same like part A, except more numbers. Domain. List them out in order. Range. Once again, for each X value, is there only one Y value? Yep. A function. Alright, now we're going to get into these different kind of graphs. You might not actually be learning these until like grade 11 math, but I thought I'd show them to you now anyways. Hey, why not? This is an extension. If you look at this y equals x squared graph, this is a graph of a parabola. It's this U-shaped kind of curve. But notice here, if I asked you for the domain, you would say, it looks like all values of x work. And you're right. So there you go, all values of x. But what about the range? Not so good in this case, right? Not all y values. It looks like it's only bigger or equal to 0. Now once again, if you don't like this formal way, then a lot of teachers are just okay with writing that part. That's good enough. And my question then is this a function? Let me draw some vertical lines. Do you see it touching one in one place? Nope. So ding ding ding, yes, it is a function as well. Alright, some more interesting graphs from D&E. Something called the square root graph. Yeah, this is what it looks like. Y equals root x. What's the domain? In this case, it looks like x has to be bigger or equal to 0. And the range? Also bigger or equal to 0. Right. Function? Yes! Nicely done. Y equals 1 divided by x. This is what they call the reciprocal graph. Whoa, crazy, crazy stuff now. Nonetheless, you can still do this. Domain. Now, interestingly enough, the graph like dips down, so it doesn't really actually equal to 0. So you could say something like this. X does not equal to 0, but all the other real numbers work. And that would be good. Okay. I guess the other way you can write this down would be x has to be less than 0 or x has to be bigger than 0. But it's easier probably to say x can't be 0. And similarly for the range, I know this is kind of hard to see, but the graph gets closer and closer to the x value, or the x-axis, but actually never touches it. So, same idea. Y can't be 0. Y must be a real number. Last but not least. Function. Yes or no? Yes. Okay, so I'll show you some crazy graphs. Nonetheless, you can still do them. Oh, let me show you 2 more crazy graphs. Once again, we're asking for domain and range, right? So domain for this one. Let's see. The x value is here. The smallest seems to be -3. Now I'm going to put an equal sign there because that's a solid dot. And the largest value is +3. And really, if I want to be more specific, I can say that all of them in between have to be real numbers. So I can do that. Or, like I said, most math teachers are okay just with that. With the range, look at the y values. And the smallest one is -2. And the largest one is 4. And you can say that in that region, y also has to be a real number. Okay? Now, how about G? This one's even trickier because there's a break in the graph. So there are actually two parts. The first part I see like this. X has to be between -4 and 1. Notice there's an equal sign on the -4, but because this is an open dot, it's just a less than sign on the 1. And then it's also this other region from 1 to 4. And of course, in those regions, it has to be a real number. The range, going from 0, and I'm putting an equal sign because I know this one is an empty dot, but this one here is solid. And same thing with the top number of 3. One is solid, one is empty. Gotta still include it. And there you go. And by the way, yes, both are functions. All of these were actually functions, because none of them actually did not pass the vertical line test. Okay, so I think we're going to conclude with example number 6 here. Going to review some stuff from before, but given the following graphs, I want you to determine the following. So there's actually two questions here, right? So let's do part A first. I think that's the easier one. You've got an equation, y equals 2x plus 3, and there's the corresponding graph. Determine the range value when the domain value is -1. What does that mean? What's the range value? That's the y value, right? When the domain value is -1, well, what's that? That's the x value. So when x is -1, the range is, the y value is, yeah, 1. Good. And if I did part 2, determine the domain value, so once again that means find x. When the range value is 3, so when y equals to 3, I look on the graph and here's y is 3, and the domain value must be 0. Okay. And similarly for the last one, finding x if f of x equals to 5. Once again, f of x equals to 5 is the y value. So looking at my graph, or looking at my equation, I see that the answer is 1. Okay, so x equals to 1. Or I could have just used the equation. Remember, 2x plus 3. If you like algebra, you replace 5 with y, or y with 5, and then you actually get the same thing. X equals to 1. It's beautiful when algebra and the visual connect and you get the same answer. Ah, so lovely. Okay, so if you can try part B on your own, I'd appreciate it. And then once you're done, come back and check, and hopefully get them all right, and then you'll be good to go. Domain value when the range value is 3. Domain value when the range value is 3. When y equals to 3. Where's y equals 3? Right here. So there's a value. I should probably do it blue. There's a value. -1. There's another value here. Oh, what's that? Maybe, I don't know, -1.25. So there could be actually more than one value. In this case, there are 2. Okay, determine the range value when the domain is 3. So when the domain is 3, the range value, yeah, that's the y value, so that's -2. And then, how about this one, f of 0? What's that mean? Oh, this means that the x value is 0. So when x is equal to 0, find the y value. And if I look at the graph, when x equals to 0, is it this open dot or is this solid dot? This is tricky. I hope you said it's the solid dot. Yes! So it's actually equal to 1. Tricky, 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 tricky. Remember, this is the value, so you're looking for solid dot. And then the last one here, find x when f of x equals to 1. Once again, f of x equals to 1. That means the y value is 1, so right here I see, right here I see, right here I see, and right here I see. 4 possible answers. -2, 0, 1, and maybe 1.5. Okay, So be careful. Find all x. Wow. Leave the trickiest question to the end. But I hope you got it. And if not, don't worry. Write down the right answer, learn from it, and apply it. See you for the next video.